Good morning. My name is Angela Lyons, and I am applying for the chemistry tutoring position. Today we're going to be looking at a problem that asks students to calculate the equilibrium constant of a chemical reaction given initial data for that reaction. Let's take a look at the problem. It says a closed system initially containing 1 times 10 to the negative 3 molar of H2 and 2 times 10 to the negative 3 molar of I2 at 448 degrees Celsius is allowed to reach equilibrium. And at equilibrium, the HI concentration is 1.87 times 10 to the negative 3 molar. Calculate Kc at 448 degrees for the reaction. H2 plus I2 yields 2HI. Alright, so we are given the initial concentrations of H2 and I2. We're given the equilibrium concentration of HI, and we're asked to calculate the equilibrium constant Kc for the reaction. Kc, that is a molar concentration, so we're going to need to calculate molarities and apply that in order to calculate that equilibrium constant. Alright, so let's come up with a plan. Our plan is to construct a table to find equilibrium concentrations of all of the species, and we're going to use those concentrations to calculate the equilibrium constant. So let's first tabulate what we know. What are we given in the problem? We're given that the initial concentration of H2 and I2, we're given the equilibrium concentration of HI, and because HI is a product, that initial concentration is 0. So we're going to fill in those values in that table. That first row, we have the initial concentration of all of the species. The second row, we don't have the change just yet. And that third row, the equilibrium concentration, we have for our product HI. So now that we have the information that's given, we can calculate the change in HI concentration, which is the difference between the equilibrium and the initial value. So the change in HI, which is shown in this line, is our equilibrium concentration of 1.87 times 10 to the negative 3 molar minus 0, that initial concentration, and we get 1.87 times 10 to the negative 3 molar. Next, we can use that change in HI concentration, and we can use the coefficients from our balanced chemical equation to calculate the changes in H2 and I2. And what we're going to be applying is mole ratios. So let's look at H2 first. So if we're starting with our change in HI concentration, which is 1.87 times 10 to the negative 3 molar, we can express molar as moles of HI per liter. If we look at our balanced chemical equation, the mole ratio between HI and H2 is 2 to 1, or the ratio between H2 and HI is 1 to 2, which is what we're going to apply over here. We have 1 mole of H2 for every 2 moles of HI because of those coefficients. The moles of HI cancel, and our change in H2 concentration is 0.935 times 10 to the negative 3 moles of H2 per liter, or molars of H2. Let's do the exact same thing for I2. So if we start with our change in HI concentration, which is 1.87 times 10 to the negative 3 moles of HI per liter, from our balanced chemical equation above, we see that the mole ratio between I2 and HI is 1 to 2. So we're going to apply that mole ratio over here. Our moles of HI cancel, so our change in I2 concentration is 0.935 times 10 to the negative 3 moles of I2 per liter. So we're going to calculate the equilibrium concentrations of I2 and H2 using the initial concentrations that were given in the problem and those changes that we just calculated. The equilibrium concentration is the initial concentration minus whatever is consumed, which is that change. Alright, so for H2, We started at 1 times 10 to the negative 3 molar. We're going to subtract out our change, that's what's being consumed in the reaction, which is 0.935 times 10 to the negative 3 molar. So we get that our equilibrium concentration for H2 is 0.065 times 10 to the negative 3 molar. We can do the exact same thing for I2. We started at 2 times 10 to the negative 3 molar, and we're subtracting out what is consumed in the reaction, that change in I2, which is 0.935 times 10 to the negative 3 molar. So our equilibrium concentration of I2 is 1.065 times 10 to the negative 3 molar. So we can use those changes and the equilibrium concentrations to finish that table that we initially started. We see that in the row where it says change in concentration, for our reactants, because those are being consumed, those are negative. And for our product, because that's being formed, that change is positive. We also can fill in those equilibrium concentrations that we just found. So now we're ready to use that information to calculate Kc. And recall that we said Kc is a molar concentration. What I have provided is a sample chemical reaction. The capital letters are our reactants and products, and the lowercase letters are those coefficients. So students already know how to calculate the equilibrium constant given that sample equation, and that's what's shown here. It's the product of the products raised to their respective coefficients divided by the product of the reactants raised to their respective coefficients. So if you look at the equation that we're working with, the H2 plus I2 gives us 2HI. We can express the equilibrium constant as HI to the second power because of that 2 as a coefficient, divided by the product of H2 and I2 because we have two reactants. And those coefficients are 1, so that's what the exponents are for those reactants. Now we just need to plug in the values that we found. Our equilibrium concentration of HI is 1.87 times 10 to the negative 3. We're going to square that because of that 2 as a coefficient. We're dividing that by the 0.065 times 10 to the negative 3 times 1.065 times 10 to the negative 3. And we get that our equilibrium constant is 51. Alright, so let's recall what we did. We calculated the equilibrium constant for a reaction, and for that reaction we were given initial data for our reactants, the equilibrium concentration for our product, and we used stoichiometry to calculate the changes in concentration to figure out the equilibrium concentrations for our reactants. Once we found that, we used the expression for the equilibrium constant to plug in that data, and we figured out the equilibrium constant for the problem. Alright, that was our problem. Thank you, and I hope to hear back from you soon.